Okay, so I'm pulling up Alex. This is chapter 8. We're doing a review. Everyone should have a note card. Write down some things on here. Single-sided note card. One-sided staple. All right. Are there any specific topics in chapter 8? I guess on the test there's going to be every topic, and this topic will show up twice. The using molarity to find solute moles and solution volume. You're going to get one you have to calculate moles and one you have to calculate volume.
Can we do this one?
This one? Yes. All right. Okay, so for this topic, I would write down all of the variations of the equation. So I'm going to use the terms that Alex uses. So they say this one is moles using solute, moles, and volume. Okay. So we need this equation. Concentration is moles divided by volume. If we move volume to the other side, we multiply both sides by volume, then it's going to be moles is equal to concentration times volume. So if we're looking for moles, this is the way we're going to find that. Concentration times volume. And then we can also solve for volume. If we divide both sides by concentration, we'll get volume. Volume is the concentration, moles divided by concentration. Okay, so this is the same equation. We're just manipulating it so we can find what we want. So there's one problem that asks us about concentration, and then one question that asks us about moles and volume, and you're going to have to do one of each of those. Okay. All right. Let's go to the topic. This one says, calculate the volume. And the volume is in milliliters. So I like to look at the box to look at the units. That will tell me the volume. Calculate the volume in milliliters of a 0.4 moles per liter aluminum chloride solution that contains 300 millimoles of aluminum chloride. Round to 2 significant digits. So on the test, it's not going to tell me how many significant digits to use. So I have to figure that out. This one has 2. This one has 3. We're going to be doing multiplication or division. So we're going to keep the least number of sig figs, so we're going to keep 2. All right. I wish this fit better. So I'm looking for volume. So I'm going to take moles divided by concentration. Moles per liter is concentration. So I'm using this equation. Moles, which is 300. Oh, I don't know why I want to put 330 really bad. This is millimoles. And I'm going to divide that by the concentration, which is 0.4 moles per liter. If I look at my units right now, millimoles won't cancel with moles. Oops. So I need to change this one to moles. Instead of writing milli, I'm going to write times 10 to the minus 3. I have just started remembering that, but if I can't remember that, then I will look at my Alex data table and look at SI prefixes. You get this on the test. So milli is times 10 to the minus 3. So anytime I see millimoles, I can change the milli to times 10 to the minus 3. Okay, so now I'm going to type this into my calculator. I have, is it 0.3? No, 300. 300 times 10 to the minus 3 divided by, I want to divide all of this by 0.4. 0.75, that's 2 sig figs, so I'm going to type it in the box. Oh, my bad. Okay, so what did I find? I forgot to do one thing. So we just found liters, 0.75 liters. Yes, the box asks for milliliters. Good. So, if I have 0.0000, so 1 liter is 1,000 milliliters. So I'm going to move the decimal 1, 2, 3. So 750 milliliters is the same as 0.75 liters. Oh, okay. This one's annoying. Let's see. Okay, so 750, and then I'm going to put it in scientific notation because I can only have 2 sig figs. Okay. All right, so this was calculating volume. We used this equation. Let's do this problem one more time and we'll find moles. Does that work? Okay, because you'll find one of each of these on the test. Moles. This is finding, again, I need to be more careful and make sure that I put the right unit in, micromoles. Okay, so I'm going to use this equation. Moles is concentration times the volume. We have 250 milliliters. I'm just going to change that right now to liters. And I'm going to, so that's volume, and I'm going to multiply that by the concentration, which is 6.97 times 10 to the minus 4. And then I have milli, which is times 10 to the minus 3 molar, millimolar. So I'm just going to times all those together, and then it's asking for micro, so I need to convert that before I type it in the box. So 250 times 10 to the minus 3 times the concentration, and then my prefix times 10 to the minus 3. Okay, I have this really small number. I'm going to put in scientific notation. Let's see. I have 4 sig figs and 3 sig figs, so I need to keep 3. 1.74 times 10 to the minus 7. This is in, I have liters times molarity, which is moles per liter. So my answer is in moles. It's asking for me for micromoles. So for 1 mole, that is 1 times 10 to the minus, or not times, minus, times 10 to the 6 micromoles. I need a lot of little moles to make 1 big mole. So I'm going to times this by 10 to the 6. And then I need, how many? 3. Well, so this is going to be 0.174 micromoles. Okay, so we've done that one twice. We've done each one that's going to be on the test. Okay, any other ones that you want to work through together? Yes?
Identify the correct sketch of a compound in aqueous solution.
Okay, this is really important. Okay, so this one we need to look for if it's ionic or covalent. So if it's ionic, it's going to split into ions. Okay, if it's covalent or if it's a molecule, it won't split. won't break. There is an exception, so not really an exception. You just have to recognize, look for NH4. If you have anything with NH4 at the beginning, that's hard to recognize that it's ionic because there's no metals. But NH4 is an ion.
Cool.
Yes. So look for that, or NH4, NO3 would be one. These are ionic. So for example, this one would break into NH4 plus and Cl minus. This one would break into NH4 plus and NO3 minus. So NH4 is one that's like, it's just kind of weird. It's kind of our weird exception. Okay, so the first one is, I look at this one and I see barium as a metal. So I know this is ionic. So I'm going to look for barium, and then I'm going to look for 2 chlorine ions floating around. This one we have to make sure that I have a 1-to-2 ratio in the solution, and I only have 2 types of elements. So let's see. This one is a 1-to-1 ratio. That's not true. I need 1 barium for 2 chlorines. This one is not true because they're not broken apart. This one looks good because I have 1 barium for 2 chlorines, 1 barium for 2 chlorines. Do you want to go through all of them, or just if we find it, we're good?
No, that's okay.
Okay. Okay, next one. This one, NH3 ammonia, is covalent. This one doesn't break apart. So we're looking for nitrogen attached to 3 hydrogens. Nitrogen attached to 3 hydrogens. That's a great model. Okay, do you want to go through more?
No, that's okay.
Okay. Okay, other ones you want to go through. So I think this is the hardest one. We did one example of these. Do you want to go through another of the boiling point question? Okay, let's do one of those. So for this one, I think this is helpful to me. I don't know, this is helpful for me. I have water, that's pure water. I have the freezing point, and I have the boiling point. This is what I think of. And then if I add anything, then it's going to decrease the freezing point, and it's going to increase the boiling point. The way so if it has a bigger molality, it's going to have a bigger effect on the boiling point and freezing point. So let's see. Before I start this one, I'm always going to put that water has the highest freezing point and the lowest boiling point. And this is confusing to me. So this might be something that I label on my note card. So the freezing point, this one goes by highest freezing point and lowest boiling point. So water is that. And water's not going to change. So you should be able to, I expect you all to get at least 0.25 on this question. Okay, the biggest effect is going to lower the freezing point the most and also raise the boiling point the most. And then the one that with the next molarity is going to lower the freezing point almost the most and raise the boiling point second, but it's third. And then the smallest molality will be closest to water. It will drop the freezing point a little bit, and it will increase the boiling point a little bit. So I think that would be helpful for me on my note card. Just the numbers get confusing to me. So, all right. Then when I do this, this is what we need to do. We need to find the molality. Molality is number of particles, number of moles of particles per kilogram of solvent. So the first thing we need to do is figure out the number of moles of particles. to find that number of moles of particles, we're going to take the mass they give us. We're going to find the number of moles by dividing by the molar mass. Then we're going to multiply by the number of particles per mole that each compound gives us. Okay. The other piece of this equation is the kilograms of solvent, which is, if we have 7.5 grams, we're going to multiply by the density first. 1 gram. I guess we're dividing by the density. Divided by 1 gram per mole, milliliter. That will give us our value in milliliters. What's happening? They give us a volume. Okay. Whoa. Let's back up. We have 250 milliliters of solvent. There we go. Now we're going to multiply by the density. 1 gram per milliliter. That will give us grams. 250 grams. Then we're going to divide by 1,000 to get how many kilograms. So for this problem, we have 0.25 kilograms. Okay, are we doing okay so far? So we take the value they give us, 7.5. We're going to divide by the molar mass to find the number of moles of this. This one is not on here, so we have to calculate it. So glycerin is 3 carbons, 3 times carbon plus 8 times hydrogen plus 3 times oxygen. So this is divided by the molar mass, and then I'm going to multiply by the number of particles. This is covalent, so there's only 1 particle. So I can multiply by 1, or that doesn't do anything. So then I have to divide by the kilograms of solvent. Oh, there's a comma. So I'm going to write that down. The first one is glycerin. I think there's a Y. I don't know. 0.3257. The next one, same thing. Take the 7.5, divide by the molar mass. Calcium chloride is in here. Multiply by the number of particles this is going to give me. This is going to give me 3 particles. I have calcium and 2 chlorines. So 3 particles per mole of calcium chloride. Then I'm going to divide this by the kilograms of solvent. Which is, so the next one is calcium chloride, 0.811. And then the last one is sucrose. So 7.5 divided by molar mass of sucrose. This one also is covalent, so it doesn't split up. Times by 1. Then divide by the kilograms of solvent. This one's really small. All right, so bigger will have a bigger effect. Calcium chloride here has the biggest molality, so this one will have the greatest difference from water. It will have the greatest difference from water. So it's going to have the highest boiling point. It's going to have the lowest freezing point. Okay, the next number on my list is glycerin. Glycerin is going to have the next lowest freezing point and the next highest boiling point. And then the last one is sucrose. It's just going to have a little bit of difference from the water. A little bit of difference from water. Hopefully I have those right. Okay. How do you feel about that one? Yes. Yes. So if it's covalent, it's only one. If it's ionic, I have to count all the particles. So this one's going to be 1 calcium and 2 chlorines. So that gives me 3. Did I multiply by 3 or 2? This one should be 3. Okay. This one is covalent, just 1. Should we open another one and we can look? Oops. Okay, this one. How many particles is this one going to give us? This one's going to give us 2 because we got potassium and we got hydroxide. This is a polyatomic ion. OH doesn't break apart from each other. So potassium breaks apart and hydroxide. We get one of each of those. This one is covalent. This one is an acid. It tells me it's an acid, so I'm going to look at the hydrogen at the beginning. Hydrogen at the beginning is going to break apart from the second thing. So this one's going to be 2. Yep. Let's try another one. This one, we've already done this one. Oh, here's another acid. H will break apart from I, that's 2. 3. 1, just doesn't break apart. How about this one? Yep. And there's 2 potassiums. So 3. 2 potassiums, 1 sulfate. Sulfate is a polyatomic ion, SO4 2-. So that stays together like hydroxide. This is staying a piece, and potassium is breaking apart from it. So the plus part is breaking from the minus part. And there's 2 plus parts. I don't know if that makes sense. I can write this one down. This one is like K plus, SO4 2-. So this is 1 piece, this is 1 piece, this is 1 piece. So 3 pieces. I know this polyatomic ion from chapter 3, I think, when I memorized the polyatomic ions. Okay, is that helpful? Do you want to do another?
Yes.
One more? Like the whole thing?
Yeah.
Okay. Oh, I don't know. We're going to try another. Okay, great. So this one, we're gonna follow this pattern again. So let's find the number of moles of particles. This is going to be 0.1 kilograms of water from my pattern. First, I'm going to choose that water has the highest freezing point and the lowest boiling point. And then I'm going to calculate the molalities. So we're going to take our mass, 7.6. We're going to divide by the molar mass of potassium hydroxide. Oh, it didn't give it to us. Potassium plus hydroxide, O plus H. And then I'm going to multiply whatever I get by how many? How many pieces?
Oh, wait, what?
So we got potassium and then hydroxide. OH is a polyatomic ion that stays together. Yep. So usually the covalent part stays together. So this is 2 times 2. Then divide by 0.1 because that's how many kilograms of solvent we have. Oh, that one's really big. So KOH is 2.7. Okay, the next one, I'm going to take my value, 7.6. Divide by the molar mass. They give us 2. They didn't give us the first one, so did I do that right? Yeah, okay. And then how many particles is this going to break into? Nitric acid. 2. The hydrogen and then the nitrate. Good. So multiply by 2. Okay, divide by 0.1. That's how many kilograms of solvent. All right. Okay, next one is 2.4. This is nitric acid. And then the last one is glycerin, 7.6 divided by molar mass. And then how many particles for glycerin? Just 1. So we could times by 1, but I'm not going to. Divided by 0.1. Okay, so this is glycerin. That's a 0. Oh, okay, so then I look at these values. This is the biggest value, so it's going to have the biggest effect. So this is going to be the furthest from water. It's going to have the highest boiling point. And then the next one is nitric acid. Oh, is this going to be in order? I've never seen this. Is this going to be wrong? This one's going to have the second highest, lowest freezing point. And it's going to be the third different boiling point from water. And then this one's going to be the last one. It's going to be the closest to water in freezing point and boiling point. Oops. I've never had it go in order. I don't know. I feel like that's going to be wrong. Okay. Okay, that's never happened to me before. All right, did that make sense? Okay. All right, other ones that you want to go over. I might pick one if you don't pick one. Another. Okay, great. That's a good one to go over. So for this topic, you can use this card, but you cannot write on this. So I'm going to check. If you wrote on this, then you have to use the Alex table. This is the Alex table. It's just easier to use the paper. But you can't use it. This is college. We gotta be serious.
Alex cases are very serious. So what is a serious face?
No writing. Wait till after the test. Actually, I can't remember if this comes up on the final, so don't write on it. Okay, so for this topic, again, this is in the Alex data. I just think it's easier to work on a paper. For me, maybe it's easier for you to use the computer. I don't know what's happening. So if I lost my paper, I can use the solubility of ionic compounds. This is the same thing, okay? All right, but I'm going to use this paper because that's just easier for me. So what I'm going to do is I'm going to trade so this is my metal and my polyatomic ion, and a metal and a polyatomic ion. These are given to me as liquids. So this is just like lab 4. What I'm going to do is I'm going to see if lead sulfate is a precipitate or if sodium nitrate is a precipitate. Only one of them will be. And then I'll type it in the box if it's soluble, or if it's not soluble. Okay, so I'm looking at lead sulfate first. So the metal and the anion are just trading. So lead is Pb, and sulfate is way over here. So that says no, that's not soluble. So it will precipitate. Yes, a precipitate forms. So it's inverse. If it says no, I'm going to push yes. And then I have to figure out the formula. Well, this is kind of nice because it gives me the charge. This is lead 2. Sulfate is SO4 2-. So I just need 1 sulfate for 1 lead. So my precipitate will be PbSO4. That looks funny. Is there a space here? No. Okay. Oh! I put on caps lock. Okay, does that make sense? Okay. So the next one, we're assuming these are soluble, so we're gonna change copper 2 with sulfide and potassium with bromide. So copper 2, let's see. Copper is Cu, copper 2, and sulfide. So it says no. So if it says no, we're gonna push yes. And then we have to figure out the charge. Both of these have a 2 charge, so we just need 1 copper for 1 sulfide. So CuS. And then the last one, sodium and nitrate. Well, no nitrates are soluble. And barium and acetate. Barium is Ba. Acetate is also soluble. So that one, does it precipitate form? No. So that's all.
Yes.
Yes. Oh, yes. Did I only look at one or did I? Yes. Okay. Both are yes, so it's no. Yes. It's inverse. Did I push the button? Okay. Okay. All right. Other topics you want to go over? We got 40 minutes. Yep, thanks. We got 40 minutes left. Is it? Oh, okay. 40 for everything. It is. Apparently. Okay, other questions you would like to go over? Okay, great. I would like to go over that one. So this one, when we are doing this problem, you're looking for, is it polar or nonpolar? Does it have OH or NH2 groups? And yes, that's what you're looking for. So this one, if I look at this, calcium chloride, this is ionic. So if it's ionic, it will dissolve in polar solvents. So you need to recognize this is a tetrahedral carbon molecule. It's nonpolar. So this cannot dissolve. This has no charges. This has a positive and a negative charge. There's no way you can get this to dissolve in something that is nonpolar. So this one is almost a tetrahedral, but it has an OH group. So it has one different group. This is polar. So calcium chloride is going to dissolve in this one better. This is methanol.
So are you matching polar with nonpolar?
You're matching ionic with polar,
And then
polar with polar, nonpolar with nonpolar. We can write a table. Oh, that's very blurry. This is what I think about. I look for, if it's ionic, then my solvent needs to be polar. So good polar solvents that often come up are water or methanol, CH3OH. Whoa. If it is nonpolar, then I look for a nonpolar solvent. So that would be like Cl4 or a long carbon chain, which is like H3C, CH2, 4 of those CH3. So this would be like hexane. That's a long carbon chain that's nonpolar. Sometimes they have like benzene. That's also nonpolar. Something like this.
You just draw that as an octagon, right? If you're doing biological.
Hexagon. Yes. Yes. Oh yeah. But yes.
It's just the shape because of the carbon.
Yes. We'll talk about that in chapter 11. Okay. The other one that I also watch out for is if my molecule has hydrogen bonding. Then I'm going to look for hydrogen bonding.
And you said OH dissolves hydrogen bonding. Well, hydroxide does have hydrogen bonding because that's how hydroxide works.
Yes. OH group, hydroxide group. Yes. H bonding. So I'm looking for something that has OH or NH2. That would be the best solvent. Or again, like dissolves like. If it has the same types of groups, then it's going to dissolve it. That would be the next best option. Okay, we're good?
Okay, so you said there's three types. There's polar, non-polar, and sorry, what was the third one?
Hydrogen, ionic. Ionic dissolves in polar. Non-polar dissolves in non-polar. Hydrogen bonding dissolves in hydrogen bonding. And then otherwise, like dissolves like, and you're just trying to find the best one. Okay, so we did that one. How about this one? We have OH groups. So anytime I have OH groups, I'm going to try to pick one that has OH groups. This one has OH groups. This one, oh, the first thing I see is this one has OH groups. So I'm going to find this one also has OH groups.
Wait, so I have a question about one that like this.
Okay, yeah, show us. You could put your Chromebook here. Sorry. That's just the lights above. Okay, so what about this molecule? What do you think?
Non-polar, so like the CH8.
Oh, this one is polar because the oxygen's on one side.
Oh yeah,
But
it's not the.
The thing that I'm going to look at for this molecule is the hydrogen bonding. This has NH2. That's going to have hydrogen bonding.
So yeah.
So look for OH or another NH2 group. So this has OH. So that's found in yeah. Yes.
So, is there like an order that you should look for? Like, if it has hydrogen bonding?
Yes, that should be a priority. Yes.
And then polar, non-polar, and
Then like similar structure. Yeah. And then yeah, polar. Yes. Usually it's polar because there's an oxygen hanging off. So the better solvent will also have an oxygen to one side. So like this one, this one's similar. If I didn't have this option, this would be a pretty good option. But because I have OH, then this is better. If I didn't have that, this would probably be pretty
So
good.
both would dissolve well. It's just
Yeah, this
the
is
first
better.
dissolve is a little bit better.
Yeah, probably. Yeah, that's our prediction. Okay, how about this one? This is ammonium. Bromine.
So you're probably the second.
Yeah, this one is the bottom one because this is ionic. This is one of those exceptions. NH4, it doesn't have a metal, but we have a positive and a negative charge.
Out of curiosity, is there a name for the top one?
Toluene.
Toluene?
Yes. Cool. Yes, I know this because my very first week of my PhD, I caught toluene on fire in the lab. And I had to give a safety presentation on how to not do that. So, that was very embarrassing, but we're all safer for that. Okay. These are OH groups. So water would be the best one. Yeah.
Wait, what was the one in the middle?
So this one would be, we would pick the methanol, or ethanol, this ethanol, because of it's polar. This is non-polar. It has lots of carbons. One side's a little different, but this would be the better one.
But I thought it was CH8.
Yes, this part of the molecule is non-polar, but we have an OH group, which makes one side, the oxygen side's gonna be more negative. Yeah. Okay. Do you want to do more of these, or do you want to do another topic? What do you want to do? Let's do this one really quick. This one is hydrogen bonding. So this looks pretty similar, but this one has OH groups. Water has hydrogen bonding. That would be better. This is a long carbon chain. NOF. They're the top green ones on the periodic table. NOF. This one would dissolve better in carbon tetrachloride. This is nonpolar. This long carbon chain is nonpolar also. This is benzene. Benzene is nonpolar. It will dissolve better in, this is hexane, long carbon chain. Okay, so that one's just being familiar. I would do lots of those, make sure you're comfortable with that topic. Okay, other topics in here you want to go over. We are down to 30 minutes left. So the other option is we could just work. Work? Okay, all right.